Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, I welcome all of you to Technical Session 9F. My name is Amok Dhamdere, and I will be moderating this session. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is a great pleasure to have all of you, to welcome all of you to the 11th International Congress on Information and Communication Technology for Intelligent Systems, ICTIS 2026. The 11th edition of this conference is being held in hybrid mode. The physical event is going to be held today in Bangkok, Thailand, and the virtual event is being held through Zoom from the 9th to the 11th of April 2026. I hope all of you will enjoy the knowledgeable and interactive sessions that we have planned throughout the day. In this particular session, we will be having 10 presentations where each presenter will be given 10 minutes for their presentation and 2 minutes for questions and answers. And on the completion of around 8 to 9 minutes, I will be raising a gentle reminder. There is another request to all the participants that all of you please stay connected with us until the closing remarks are given. And if you have any queries or updates, then you can write it to me in the chat box. Before we begin, I would like to introduce our session chairs for this session. So our first session chair is Dr. Muhammad A. Tawhid. Dr. Mohammed A. Tawhid is a full professor of mathematics and statistics at Thompson Rivers University, Canada, with over 26 years of academic and research experience. His work focuses on applied mathematics, particularly optimization and computational intelligence, with research spanning AI, data analysis, modeling and simulation, big data, and image restoration as well. So we welcome you, and I request you to give us your opening remarks.
Hi everyone. It's a pleasure to have you all of you today here and to be with you here. It's a real pleasure.
Thank you so much, sir. It's great to have you with us. Our next session chair is Dr. Ajay Kumar Sharma. Dr. Ajay Kumar Sharma is an associate professor and MTech coordinator in the Department of Computer Science and Engineering at Gitanjali Institute of Technical Studies in Udaipur, Rajasthan. With over 18 years of teaching experience, he has presented numerous papers in national and international journals, conferences, and symposiums. He has also served as a reviewer for more than 15 papers in IEEE and Scopus indexed conferences and journals. Sir, we welcome you, and I request you to give us your opening remarks.
Yes, sir. Thank you, sir. Respected session chair, a very good afternoon to all the participants. It's my great privilege and honor to serve as a session chair for this session of the International Conference on Information and Communication Technology for Intelligent System. I think this conference brings together brilliant minds, innovative ideas, and cutting edges research that continue the shape future of intelligent technologies. At the outset, I would express my gratitude to the entire organizing and core team whose dedication, planning, and hard work have made this event possible. I would like to extend my appreciation to our moderator for efficient coordinating the session and ensuring a smooth flow of discussion. A special note to very special note to Dr. Amit Joshi sir for his valuable support, guidance, and contribution, which has significantly enriched this conference. As we begin the session, I encourage all the participants not only actively engage and share insights, but also clearly highlight the novelty and unique contribution of their research, as it is as a very essential for advanced knowledge. With this, let us proceed this session. Thank you. I wish everyone a highly insightful discussion ahead. Thank you, sir.
Thank you. Thank you so much, sir. Without any further ado, we would now move on to our presentations for this session. So the first presentation will be done by Soji Binu Matthew from the Karunya Institute of Technology and Sciences in India. And the title of the research paper is A Hybrid Unsupervised Approach for Fetal Brain Anomaly Detection Based on Image Quality Analysis and Convolutional Autoencoders. Ma'am, I request you to start presenting, please.
Afternoon, everybody. Can you hear me? Am I
Yeah.
audible?
Yes, ma'am.
Yes,
You are
yes, yes.
clearly audible.
Okay. I will share my presentation slides with you.
Sure.
Hope you can see my presentation.
Yes, ma'am. Your presentation is visible. You can start presenting.
Thank you all. So let me start. Good afternoon, everybody. Welcome you all for my presentation. I am going to present my research topic on a hybrid unsupervised approach for fetal anomaly detection based on image quality analysis and convolutional autoencoders. Let's see an overview of my presentation. So let's start with my presentation. As you know, fetal brain development is a complex process, and abnormalities can cause neurological disorders. Early detection of anomalies can provide timely medical intervention. Ultrasound is the most commonly used modality for fetal brain assessment. Image quality is often affected by various motion artifacts or noise or acquisition variability. Manual analysis is time consuming. And as you know, fetal brain anomalies are rare and subtle, and labeled data set availability is very limited. So there is a need for a fully unsupervised, automated, scalable anomaly detection. So let's see the abstract. To overcome these challenges, we propose a fully unsupervised framework for fetal brain anomaly detection without labeled data set, as labeled data set for fetal brain anomalies are scarce. Image quality metrics like Laplacian or standard deviations are used to identify the acquisition-related anomalies like sharpness, brightness, or contrast. Convolution autoencoder, CAE, learns from the normal fetal brain structural patterns and detects the abnormalities using reconstruction error. Percentile-based thresholding helps to understand adaptive anomaly detections without manual tuning or supervision. So this hybrid framework identifies multiple fetal brain anomalies for improved prenatal care. So let's see the earlier work which is done, and we have seen that early detection of fetal brain anomalies are critical for diagnosing central nervous system anomalies. The subtle nature of fetal anomalies and the complex nature and the limited labeled data set limits the effectiveness of supervised deep learning methods. By applying quantile or percentile-based thresholds on image quality metrics helps to detect anomalies without labeled data set. Integrating image quality along with CA-based helps in providing a robust hybrid framework for unsupervised fetal brain anomaly detection and clinical assessment. Let's see the data set which we used is publicly available Kaggle data set, which consisting of 2D grayscale ultrasound, fetal head and image segmentation. The acquired data set is undergone through various pre-processing methods, like it is resized into the size of 128 by 128 pixels for uniformity and noise reduction. The pixel intensities were normalized to a range of 0 to 1 to ensure consistency for further analysis. So we can see some pictures of the normal fetal head images. Now, when we move to the image quality metric anomaly detection, there are various image acquisition related anomalies are present in the images which is acquired through the ultrasound. Laplacian variance is used for identifying the blur anomalies. Mean intensity is used to identify the brightness, whether it is a dark anomaly or a bright anomaly. Standard deviation is used to identify the contrast image. Percentile-based thresholds like 5th percentile and 95th percentiles are used for the unsupervised anomaly detection. Now let's move to the Laplacian variance. It detects the image acquisition anomalies, basically the blur images. It is calculated using variance of del square I, where del square I represents the second spatial derivative. Images below the 5th percentile were classified as blur anomalies. We can see some blur anomaly of fetal head images. Let's move to the mean pixel intensity, which is used to identify the brightness related anomalies, whether it is a dark or bright images using the formula. Mu is 1 by n of sigma IXI, where IXI is the indexity value of the pixel and n is the total number of pixels. Intensity below the 5th percentile is considered as a dark anomaly, whereas above 95th percentile is considered as a bright anomaly. Let us see some of the dark and bright anomaly of fetal head images. Now, these are the image acquisition anomalies determined using the image quality metrics. Now, autoencoder CAE is used to learn the normal patterns of the fetal images, and it identifies the structural anomalies using the encoder and decoder. The encoder compresses the images, fetal heads, and it learns the compact representation of the normal fetal head images. And the decoder reconstructs the images, and using the reconstruction image, we can identify the anomaly in the structural fetal head images. So let's move to the structural anomaly detection. It is calculated using mean squared error, which is 1 by n of sigma IXI minus I dash XY the whole square, where IXY denotes the pixel intensity of the original image and I dash is of the reconstructional image, and n is the total number of pixels. So images with high reconstruction errors, like above 95th percentile, indicate structural anomalies. So let's go through some of the images of fetal head with structural anomalies. Now, model is validated because it is we are using unlabeled data set. Only qualitative evaluation is possible. Mostly quantitative evaluations, we need labeled data sets. The model is validated through the reconstruction error analysis, where the high errors images is identified as structural anomalies. Then there is using the qualitative evaluation using image quality matrices help to identify the blur, dark, bright, or low contrast fetal brain anomalies. And structural percentile-based thresholding helped in identifying the blur image, like 5th percentile below images are considered as blur or contrast, low contrast images, whereas the images above 95th percentile are considered for too bright images. Now, when you go through the result, the final anomaly classification is done based on both the structural anomalies and based on the image acquisition anomalies. The structural anomalies are given highest priority, followed by the image acquisition anomalies. Images that does not exhibit any of these anomalies is considered as normal images. So let's have a table distribution of the fetal anomaly classification, total of a 2000.
Excuse me, ma'am.
Yes.
Just a reminder, you have 2 more minutes of presentation time left.
200. understood. 2,333 fetal head ultrasound images are analyzed, and this is the table showing, and the graphical representation of the anomalies are given to you. And to conclude, a hybrid unsupervised anomaly detection model is given by integrating deep learning CAE with image quality metrics for fetal head ultrasound images. CAE is used reconstruction errors to identify structural anomalies, and image quality metrics like Laplacian or mean index intensity and standard deviation is used to identify image acquisition related anomalies. So the future work is incorporating a labeled validation using quantitative evaluation methods like F1 score or sensitivity or specificity. We can integrate advanced generative models which can improve further detection performance. And integrating multimodal fetal imaging is helps in enhancing the fetal neurodevelopment assessment, and various AI techniques can be used for getting better insight into the anomaly detection. And these are the references I have used. Thank you for the listening my presentation.
Thank you so much for presenting, ma'am. I now request our session chairs if they have any questions for you.
Hi, yes, I have one question here. Thank you for the nice presentation here. I haven't seen you to compare with other approach to say, oh, my approach here is outperform or better than others. Did you compare with other approach in literature or even in deep learning?
Yes, we have compared with other anomaly detection methods like deep learning methods, and we have seen that using these hybrid approaches gave a better identification of anomaly detections, which is explained in the text, which is in the paper I gave, that this gives better anomaly detections compared with other deep learning models.
Okay, thank you.
Thank you, sir.
Dr. Sharma, any questions for our speaker?
Ms. Venu,
Yes, doctor.
what is the size of your data set?
It is the fetal heads are 2,000, about 2,000 fetal heads are used in that one.
How you differentiate between the structural variance and unstructured? No. Structured and unstructured anomalies.
The structural anomalies are detected using the reconstruction method, using the mean squared error analysis.
How you calculated F1 score?
How you
calculate F1 score?
I cannot calculate F1 score because I have used an unlabeled data set. I cannot calculate F1 score or anything.
Just told me that I am calculating the F1 score. F1 score.
No, mean square error deviation is used for reconstruction analysis. As it is an unlabeled data set, I cannot calculate the F1 score, doctor.
Why you specially use Laplacian variance?
That is to identify the blur anomalies.
Okay. Thank you.
Thank you, doctor. Thank you so much.
Thank you so much for presenting, ma'am. We can now move
stop
on.
my sharing.
Yeah, sure.
Thank you. Thank you so much.
We now move on to our next presenter for this session. So the next presentation will be done by Mohammad Mudassir of the Christ deemed to be University in India. And the title of the research paper is A Platform to Digitally Sign and Verify 3D Graphic Models. Sir, if you are present, I request you to kindly unmute yourself and start presenting. Okay, I think he is absent at the moment. We can move on. So the next presentation will be done by Gauri P. Nair from the APJ Abdul Kalam Technological University in India. And the title of the research paper is a kit-based visual inertial odometry framework for autonomous underwater vehicle positioning. Ma'am, if you are present, please unmute yourself and start presenting.
Yes, I'm present. I will share my screen.
Sure, ma'am.
Is it visible?
Yes, it's visible and you're audible as well, so you can start.
Okay. So, good afternoon, respected panel and everyone present here. So, myself, Gauripi Nair, I'm here to present my team's research paper that is a kit-based visual initial odometry framework for autonomous underwater vehicle positioning. To give you an introduction about this paper, so autonomous underwater vehicle or AUV are used in exploration in the underwater fields such as monitoring and inspection. But what happens in underwater environments is that it is GPS denied, which makes this localization very difficult. So we go for there are traditional methods do exist, but such as acoustic method using sonar and DVL, that is Doppler velocity. But what happens is that these methods are very costly and it depends on external infrastructure. So we are doing this with the approach of visual initial odometry, that is VIO, which is a combination of both camera as well as the IMU data for localization. So IMU meaning initial measurement unit. It is basically a sensor which is embedded on the AUV to get the acceleration and the gyroscopic data of the AUV. So from this, we are able to go for a more reliable and low cost positioning approach. So our problem statement is to achieve an accurate positioning of the AUV in GPS denied environment using a VIO. Even using VIO, we are prone to dynamic underwater conditions and sensor uncertainties. So our proposed methodology, we propose AKIT VIO, which is an adaptive visual initial odometry framework. What it does is that this system combines both camera, which is for the visual features, which is coming from the AUV, and the IMU, which is the most motion estimation, which is the initial data coming from the sensor. So our AKIT VIO is actually a closed loop state estimation for underwater positioning. For doing so, we are using extended Kalman filter. Extended Kalman filter is a mathematical algorithm which is used for state estimation. So what this does is that it combines the high rate IMU data, which is about like 100 to 200 hertz, with a low rate monocular camera data, which is around 1 to 10 hertz. So this fusion is done using the EKF and which predicts the position of the AUV. Along with this, what we have introduced is a learning-based adaptive model called set transformer, which dynamically adjusts the process noise. So noise is basically the drift which is being accumulated. Like if you are taking a sensor, it is prone to error. So this error would cause a drift in the AUV positioning. To adaptively understand the drift and to adjust the noise, we are using a set transformer rather than using a fixed noise assumption. So this is our overall system architecture. For a brief explanation, the left side you can see our two inputs are IMU data and visual data. IMU data is used for extracting the motion features and the visual data is used for extracting the visual features using various techniques. So from the IMU data, it is done in the EKF, which is used to predict the state of the AUV. And this state will be represented in a 6 DOF pose. So 6 DOF is basically how an object is being placed in a three-dimensional space. And in visual features, we are taking the visual features and we are calculating innovation. So innovation is basically a difference between the predicted as well as the observed pixel. So what it helps us to understand whether to depend on the IMU prediction or to go for the visual side updation. So from this, we are able to, and these values such as innovation and the motion contest is being given to the set transformer. Set transformer is the one who does dynamically adjust the process noise. It would scale the process noise and give it back to the EKF so that it could dynamically adjust and reduce the error drift. This is the overall what the system does. So moving forward, to understand more about EKF, so EKF, as I told earlier, this is a mathematical algorithm which is used for estimating the vehicle state, its position, its velocity, and other factors. So entire prediction is being done using the IMU measurement. But what happens in IMU measurement is that it is a high frequency, and it gives a continuous motion of the data, but it accumulates drift over time. To reduce this drift, we are depending on the visual measurement, which gives us the geometric constraint through feature observation. So with this, we will calculate innovation, which gives us an idea whether the prediction is right or whether to go for the visual measurement update. So the EKF is basically doing this fusion of the IMU as well as the low rate camera correction to achieve a stable and consistent localization. So our next part of our implementation is the visual front-end pipeline. So as we know, we extracting images from the AUV, which is the monocular images. So these images would be having low visibility and turbidity due to the underwater condition. So we have to design it in such a way that we are able to handle such conditions. So there are processing steps that is happening here. First one is image enhancement. Image enhancement is done using like contrast enhancement and also hazel removal. And then we are doing feature extraction. So feature extraction is very important. We are doing this using a hybrid approach, which is combining ORB plus GFTT. ORB is basically is a technique that is oriented, fast and rotated brief. It is actually a technique which is used to capture the detected feature as well as the surrounding pixel, so that even if the AUV rotates, we will still be able to detect the feature. Along with another technique called GFTT, it is a good feature to track technique. What it basically does is that it helps to it's used for corner detection. It's a threshold based approach. So from this we are extracting feature, and this feature is matched with the previous features, and from this all the outliners are being rejected to get a more stable motion. And this outliner rejection is done using ransack based approach. So what ransack does is that it creates a model for understanding what are the best position, and all the points that is coming outside that model is being rejected. Then what we do is a 3D landmark triangulation, which is actually to convert the 2D points to 3D points. And from this, we are getting two important features, that is innovation and Kalman gain. So innovation is basically the uncertainty estimation, which the difference between the predicted and the observed pixel. Whereas Kalman gain tells us how much to correct. It tells us whether if the Kalman gain is really high, it tells us to go for the visual update. If the Kalman gain is low, it tells us that to rely on the IMU prediction itself. So our novelty, basically what we did is that our key innovation is the adaptive covariance modeling. So as I told earlier, EKF is performing based on noise, that is process noise and measurement noise. Process noise is coming from the sensors, whereas measurement noise is coming from the images. So this would lead to a covariance mismatch due to the varying visual quality and also non-stationary motion of the AUV. So which will create an overconfidence to the model, which accumulate the drift. So our proposed innovation is to bring a learning-based adaptive process noise model. So what we did is that we used a set transformer to dynamically scale the process noise covariance, that is QK. So how we scaling it is basically depending on three factors, that is the gyro noise, acceleration noise, and also the bias noise. So we are getting a scaling feature, which we will give back to the EKF to dynamically adjust the noise. So our set transformer has two major input, that is a motion contest from the IMU features and also the visual features, that is the innovation. So we are using a LSTM, that is temporal encoder, for understanding the motion dynamics, and set transformer is used for feature relationship. Why we are using set transformer is because our model is permutation invariant, that it is ordering is not there. So in order set would come. So to understand the relationship between the feature, we need a set transformer rather than a normal transformer. So what it basically
Excuse me,
does.
ma'am.
Okay.
Just a reminder, you have 2 more minutes of presentation time left. Thank you.
Okay. So the key contribution is that if the EKF makes the state EKF makes it more adaptive rather than static. So how we did this, we experimented this all on a simulation environment called Gazebo with ROS. So here we had the monocular camera as well as the IMU. And we used the ground truth from the simulation to evaluate our model. So for trajectory evaluation, what we done is that we did it using Gazebo underwater simulation. So in here, our AUV traveled around 695 meter at 60-meter depth. What we understood that at over long intervals, we depend more on the initial data because the visual correction are being less. This is actually a constraint due to our simulation side. Our visual updates are pretty low, so our drift accumulates between the visual updates. But what we observed is that even though the drift appears, our estimation is remaining stable without any divergence. Our system is not having any explosion. It is going in a stable motion. And we did it with a position and versus time calculation, and we saw that when it travels around 695 meters, it is having an average error of 149 meters. So it is due to the visual correction reduction, and wherever the visual correction is coming, we can see that our drift is reducing significantly. So we did a comparison between the fixed as well as adaptive AKIT. So wherever the fixed noise is being used for EKF, in extreme motion, that extreme dynamics of water, it is having a very high divergence, whereas the AKIT is bringing it down to about 99% improvement is there on the AKIT side. And for a stable motion of the underwater, when there is a 1 or 2 meter divergence in the EKF, fixed noise EKF, or adaptive is reducing it to about 18.3, that is 82%. And for typical motions, we are also having significant improvement, about 51%. So from all this, we could observe that our adaptive AKIT was performing in high drift reduction rather than a fixed EKF. So our conclusion is basically we proposed AKIT VIO for positioning of AUV in GPS denied environment and integrated with the adaptive based noise scaling with the transformer. And we overcome the limitation of the fixed noise VIO, and we achieved a stable estimation. And the future work, we are validating using real-world underwater data set, and also to also make our measurement noise side also adaptive, rather than just process noise side. Thank you.
Thank you so much for your presentation, ma'am. I now ask our session chairs if they have any questions for you.
Thank you for the talk here. I appreciate your talk here. So you mentioned about how to predict predictive models. Can you talk about how you what kind of model for your prediction here you are using?
So we are using EKF, that is an extended Kalman filter. So what it basically does is that it predicts the from the IMU data we are getting, we already know the position, velocity of the vehicle and acceleration. So from this, we are actually using different equations like mathematical equations for orientation and rotation. We are using these equations for predicting the motion.
All right, thank you.
Thank you, sir.
Dr. Sharma, any questions for her?
Miss Gauri,
Yes, sir.
nice presentation. No?
Thank you.
Question is that how you handle noise and drift in IMU data?
Sir, so what we are actually having is that in IMU data, we are taking a sensor drift is accumulating. So we are taking consideration of this drift. So wherever, so the process noise is there, that is the value QK. So wherever this noise is coming, we are adaptively scaling that noise so that the noise would not remain the same, because we are in underwater, so conditions are highly dynamic. So we cannot just rely on a fixed noise. So instead, we are using this set transformer to dynamically understand how the noise are changing. So that's how we are fixing the noise from the IMU sensor.
And next question is that what sensor you use in your system?
So we are using two of them, which one is a camera, that is a monocular camera. It is a low complexity camera. And then we are using a sensor called IMU, that is initial measurement unit.
Thank you.
Thank you, sir.
Thank you so much for your presentation, ma'am. We can now move on to our next speaker. So our next speaker is Zubair Zalant from the University Malaya in Malaysia. And the title of the research paper is By LSTM-based TF complex masking for multi-source noise suppression. Sir, I request you to kindly unmute yourself and start presenting, please.
Good afternoon. Good afternoon. Can you hear me?
Yes, sir. Very good afternoon. You are clearly audible.
Okay. Let me share my screen.
Sure.
Uh,
Your screen is visible, sir. You can start presenting.
okay. Good afternoon, everyone. I'm Zubair Zaland, and today I'll be presenting our work on bi-LSTM-based complex spectral masking for speech enhancement. This work focuses on improving speech quality and intelligibility in challenging, noisy, and reverberant environments using deep learning techniques. Speech signals in the real world environment are often degraded by additive noise, such as environmental sounds or competing speakers, as well as reverberation caused by room reflections. These degradations significantly reduce both intelligibility, measured by STOI, and perceptual quality, measured by PASC. Traditional signal processing methods struggle, particularly in non-stationary and multi-source noise environments. This motivates the use of deep learning approaches which can learn adaptive and data-driven solutions. Conventional approaches like spectral subtraction and Wiener filtering have several limitations. They assume stationary noise and operate only on the magnitude spectrum, completely ignoring the phase information, which often leads to audible artifacts. More advanced spatial methods such as beamforming and RETM, the relative transfer matrix, require accurate spatial modeling that are sensitive to challenging acoustic conditions. So the key challenge is to design a method that is robust, adaptive, and capable of preserving the natural structure of speech in real-world scenarios. The key motivation comes from three observations. First, phase plays a critical role in speech reconstruction, but is often ignored. Second, magnitude-only enhancement introduces artifacts such as musical noise and distortion. And third, the speech is inherently temporal, meaning that context across time is essential. Therefore, we need a model that can learn time-frequency relationships, capture both past and future contexts, and adapt to real-world environments. To address these challenges, we propose a bi-LSTM-based complex spectral masking approach. The model operates in STFT domain and predicts a complex mask consisting of both real and imaginary components. This mask is applied to noisy spectrum, and the enhanced signal is reconstructed using STFT. This enables joint enhancement of both magnitude and phase. Here's the pipeline of the overall system. We first transform the noisy speech into a time frequency domain using STFT. The features are then passed to the bi-LSTM model, which estimates a complex mask for each output channel. This mask is applied to the noisy spectrum, and finally, the inverse STFT reconstructs the enhanced speech signal. The model consists of bidirectional LSTM layers that process the sequence in both forward and backward directions. This allows the network to capture both past and future context. The bi-LSTM output is then passed through fully connected layers to estimate the real and imaginary components of the mask. This design enables context-aware enhancement across time frames. Key contributions of this work are as follows. First, the complex spectral masking, which enhances both magnitude and phase. Secondly, bidirectional temporal modeling, improved context awareness. Next, the channel-wise mask prediction, which allows better handling of multi-channel input. This allows the algorithm to produce multi-channel denoised outputs, which can then be used or integrated with frameworks with multi-channel post filters as well. And finally, a fully data-driven adaptive framework that does not rely on fixed assumptions. Compared to traditional methods, our approach does not rely on stationary assumptions and does not ignore phase information. Compared to the spatial filtering methods, it is less dependent on precise acoustic modeling and is more robust to environmental changes. Overall, it provides a more flexible and reliable solution for real-world speech enhancement. For evaluation, we use noisy reverberant speech mixtures. The model is trained using a combination of spectral and time domain loss functions. The performance is evaluated using PESC for perceptual quality and STOI for intelligibility. Here we present the experimental results. We observe that improvements in both PESC and STOI are compared to the baseline methods. This indicates that the proposed methods model not only improves speech quality and also enhances intelligibility across the board, across different SNR values. These results validate the effectiveness of complex masking and temporal modeling. The improvement we observed can be explained by two key factors. First, complex masking allows accurate reconstruction of both magnitude and phase, leading to more natural sounding speech. Second, BiLSTM captures temporal dependencies, which improves consistency and reduces distortion in time. And the model performs particularly well in non-stationary noise and reverberant environments, where the traditional methods typically struggle. However, these improvements have some trade-off. The model has higher computational complexity and may require optimization for real-time application. Additionally, its performance depends on the diversity and quality of the training data. Overall, the proposed methods achieves a strong balance between performance, robustness, and adaptability. In conclusion, I present a BiLSTM complex spectral masking approach for speech enhancement. The method effectively captures both spectral and temporal dependencies and significantly improves the performance over traditional approaches. This is particularly well suited for real-world and noisy environments. In future work, we plan to focus on real-time and low-latency implementation. We also aim to integrate the model with speech recognition systems, explore transformer-based architectures, and improve generalization across diverse environments. Thank you for your attention. I'd be happy to take any questions.
Yeah, thank you so much for your presentation, sir. Dr. Tauhid, any questions for our speaker?
Thank you for a nice presentation here. So
Thank you.
I have two questions here. The first one, why you are using bidirection in particular? Is there any, what's the reason to use bidirection for LTSM?
Okay, using BiLSTM basically allows us to keep the context of the signal in check. working on both past and future frames in context to compute a mask for the current frame in STFT domain. We also tried the same method or the same type of implementation, the context awareness with the capsule networks, but it did not provide similar output.
I see. So you mentioned about for the conclusion about the strengths of your method here. Can you tell me what is the drawback of your method here?
Yeah, currently it is enhancing speech in such a way that it is creating or making the difference between the noise and the speech more clearer, much more clearer, but it is not addressing the reverberation uh, in time as such. So in our future work, we will also be working on a different head in this architecture, which will be specifically designed to check for the late reverberation in the signal.
Sure. Thank you. Thank you.
Thank you.
Dr. Sharma, any questions for our speaker?
Hello.
Yes,
Hello.
sir.
First of all, nice presentation.
Thank you.
How your model handle multiple noise sources simultaneously?
Uh, it is handling, it is trained on multiple noise sources. Right now, have, as evident in the paper, that we have two types of noises. Firstly, the environmental noises, which is which was collected from various noise data sets. It has different types of noise, such as cafe noise, indoor and outdoor types of noises. And secondly, it has the ego noise, which is the noise coming from the devices. So the model is trained on both noises simultaneously.
And what is your data size?
The data size, it is 21,000 files of each of length 14 seconds on average. And these are pairs of clean and noisy files for training.
Last question is how your model handling overfitting?
The overfitting actually it is the various loss functions, they are making sure that the overfitting does not happen.
No issue. Thank you.
Thank you.
Okay, thank you so much for your presentation, sir. Presentation would be done by Kavita Gaura from the Chaitanya Bharati Institute of Technology in India. And the title of the research paper is MFHSI Net, Adaptive Spectral Spatial Fusion via Selective State Space Modeling for Hyperspectral Image Analysis. Ma'am, if you are present, please unmute yourself and start presenting.
Yes, sir. Good afternoon, everyone. I'm sharing the.
Sure, ma'am.
Uh, I hope my screen is
Ma'am,
visible,
your
sir.
screen is
Yeah.
visible, but it is a little zoomed in. If you can zoom out a little bit, we can see the entire thing.
Okay. Give me a minute, sir.
No, ma'am,
Ah,
the plus and minus sign that you see
yeah.
It is
just above your
PDF. It is
presentation.
PDF form. It is in PDF form.
Yeah, it should not be
Okay,
in
it's
PDF
in a
form,
PDF
sir.
form. Okay,
Yes, sir.
sure, ma'am. You can start presenting then.
Yes.
Thank you.
Yes, sir. Good afternoon, everyone. This is Kavita Gaura from CBIT, India, and the title of our work is MFHSI Net Adaptive Spectral Spacious Fusion via Selective Space Modeling for Hyperspectral Image Analysis. So here this work it is focusing on improving classification accuracy while maintaining computational efficiency for real world applications. So coming to the outline, I will be going through the introduction and motivation, proposed architecture, HISS fusion, and the proposed architecture, experiment and the results, and the conclusion. So, what is the motivation behind this one? Why hyperspectral images? So, what is the use of hyperspectral images? So, these hyperspectral imaging captures detailed spectral information across hundreds of contiguous bands, enabling precise material identification. It has important application in areas such as agriculture, environmental monitoring, and urban analysis. However, these hyperspectral images data comes with the several challenges, including high dimensionality and also the high dimensionality and the spectral redundancy, spatial variability, and increased computational cost. And but with this, the advantages are also there. So this, uh, though the spatial information is crucial for accurate classification, many methods do not effectively utilize it. So therefore, there is a need for models that can efficiently combine spectral and spatial information together, and at the same time while maintaining the lightweight. So that's why here the main objective is to develop a lightweight spectral spatial fusion framework using selective state space modeling to achieve efficient and accurate hyperspectral image classification. So if we see the limitations of the existing models, so there are few of the limitations. So here, if at all we want to summarize the existing approaches, so here we can summarize what are the limitations with the existing models. Like if we use CNNs, what are the limitations? If we use transformers, what are the limitations? If we use SSM based methods, what are the limitations? So here these traditional methods like SVM and the sparse representation, they rely mainly on the spectral features, but at the same time they are ignoring the spatial context. With the HSI, we are trying to capture both the things. So this limits their performance. And coming to the CNN based methods, they improve this by capturing the local spectral and the spatial features, but they are still limited in modeling for the long range dependencies. And the transformer based models address this issue by capturing the global context, but they suffer from the high computational complexity. So that's why most recently these state space models like Mamba provide efficient linear time modeling, but many existing architecture remain complex. So therefore, there is a need for a lightweight, efficient model that can effectively fuse spectral and spatial information with low computational cost. And this gap motivates our proposed this MFHSI. And here, coming to the problem statement. So before going to the architecture, what is the problem statement? The problem statement is here, as we know, this hyperspectral image, it can be represented as a three-dimensional cube, wherein the H, W, and the B will be there. H and W will represent the spatial dimension, and B represents the number of the spectral bands. So the task is to assign a class label to each pixel in this particular image. So to achieve accurate classification, the model must effectively capture both the spectral dependencies across the bands and the spatial context within the local neighborhoods. So at the same time, it is also important to maintain the computational efficiency for practical deployment, because the size of these HSI images, it is very huge. So therefore, our objective is to design a lightweight model which can efficiently learn spectral spatial feature and perform the accurate classification. So this is the architectural diagram. So here in this particular work, this MFHSNet, a lightweight dual work framework for hyperspectral image classification, the main idea is to separately learn the spectral and the spatial features and then combine them together, and in this way we are going to capture both the interband dependencies while the spatial branch focuses on the local structural information. So these features are then combined using the Mamba enhanced attention fusion module, which integrates state space modeling, cross attention and adaptive gating. So finally, the classification head is used to generate the pixel-wise predictions. So this design enables accurate classification while maintaining low computational complexity and the efficient inference. So here, the input to the network is a patch extracted from the hyperspectral image, and the model consists of the two parallel branches, the spectral branch and the spatial branch. And then the output from both the branches, and they are combined using this particular Mamba enhanced attention fusion module. And in this module, features are first concatenated, processed using the Mamba block for efficient global dependency modeling, and then cross attention is applied to refine the interaction between the spectral and the spatial features. Finally, an adaptive gating mechanism balances the contributions of these features. So the fused representation is passed through global average pooling mechanism and the fully connected layer to produce the final class prediction. So here is our patch-based input representation. So this is belonging to HW and to the data set, wherein we are having 3 dimensions and extract the spatial patches, and this is going to preserve the spectral as well as the spatial context. And so this is a dual branch feature extraction. So both the spectral branch is taken into consideration and the spatial branch is taken into the consideration. The output is a combination of the spectral and the spatial branch. And then here the lightweight convolutional modeling is used, wherein we are making use of the stack 3 by 3 convolution with the ReLU, and efficient local feature extraction is done. It maintains lower parameter complexity. And then as we have just discussed about the architecture overview and the feature extraction, and uh, here is the overall the pipeline. So in this one, the input histopathology image, it will be used, and that in that one the patch embedding is done to get the feature F0, and then F0 is passed through the hierarchical backbone, which will give us the features F1, F2, F3 and F4, and then that is passed through convolutional SSM blocks to give the G1, G2, G3 and G4 features, and then that is passed through the hierarchical state space fusion to give these, and then Z3 is passed through the global representation learning to get the Z final, and then Z final is passed through the classification head to get the final prediction. So here is the experimental setup and the data set. So to evaluate the model, whatever is developed, it is tested on it is trained on the 9 widely used hyperspectral benchmark data sets covering. So these are the 9 data sets which are used mainly mainly used as the hyperspectral benchmark data sets covering different types of the scenes. For pre-processing, we use the patch-based approach with the patch size of 15 by 15, and the data is normalized using min-max scaling, and the reflection padding is applied to preserve boundary information, and the data set is again split into 80% for the training and 20% for the testing. And we have trained the model using the Adam optimizer with a learning rate of the 10 to the power of -3 and a batch size of 128 and per 100 approx, and the performance is evaluated using the overall accuracy, average accuracy and the kappa coefficient. And these all the experiments, they are conducted on the NVIDIA RTX A4000 GPU. And here the state of the art comparison across the HSI benchmarks. So here the comparison is done with the CNN based model, transformer based model, MLP based model, SSM based model and MF HSI nets in comparison with the others, and it has shown that the with the various data sets, the accuracy with the MF HSI net, it is more across all the data sets, almost across all the data sets. This has performed well. And
Excuse me, ma'am.
Yes, yes.
Just a reminder, you have 2 more minutes of presentation time left. Thank
Okay,
you.
okay. And here the class-wise performance across the benchmark hyperspectral data sets, it is shown, and then the kappa coefficient also compared to all other on all the data sets. This has performed in a better manner compared with the other methods. And in addition to the accuracy, our model is also computationally efficient. It uses fewer parameters and it requires a lower number of the flops and achieves faster inference time, and this makes it suitable for real-time and resource-constrained application. Overall, we can say the results demonstrate that the approach, whatever we are using, it captures both the spectral and the spatial information while maintaining the efficiency. So here the component wise evaluation of this on the this particular data set. So here it is overall accuracy, spectral and the spatial branches. So it provides complementary feature representation, and MAF module enables adaptive spectral and spatial fusion and provides largest performance gains, and full model achieves the best results. And coming to the conclusion, here, we can say the proposed MFHSINet is a lightweight dual branch framework for hyperspectral image classification. It combines spectral and spatial branches to capture complementary feature representation and introduces Mamba enhanced attention feature for adaptive spectral spatial integration, and it achieves state of the art performance for these accuracy measures with these performance measures with improved efficiency across multiple benchmarks. And the future directions are to extend to large scale and high resolution HSI data sets, and also adapt for segmentation and object detection tasks, and it can be explored with multimodal remote sensing data fusion, and it can be used to develop the real time and edge deployable HSI models. So as the data whatever we are using, it is of huge uh, size, so that is the problem. So for that we are only making use of the extraction of the features whichever are more important. Yeah, so this ends the presentation, sir.
Okay, thank you so much for your presentation, ma'am. I now ask our session chairs. Dr. Tohid, any questions for our speaker?
Yes, thank you for the nice presentation here. So I have one couple of questions here, but maybe just the first one here is uh, uh, the complexity of your model here. How better compared to the existing one that you mentioned at the beginning?
Sir, it is linear in scale, sir. It is order of n. Like if the transformer model is taking order of n square, so this R model is taking order of n.
Yes, I know that. So what is n?
N is the parameter, sir.
Yes, I know, but is that the operations or?
Based upon the number of the features whatever we are collecting.
Okay. So when you use feature extraction there, and then you are using, you combine after that Mamba, what's called the other approach. So why you can use after you are using feature extraction, you can use feature selection. If the data set is big, you can generate a subset, and then you can apply after that your the other approach, or you haven't used feature selection.
Uh, Actually, sir, here the main aim of this hyperspectral images is it is going to capture each and every minute feature whichever are lying around the mix pixel. So that's why whatever data we are going to get, that will be in the form of the bands, and here from that we are going to select the main features. So for that we are making use of the Mamba technology. So this Mamba uses a state space modeling with linear complexity, so with which we are enabling efficient long sequence modeling with lower memory and the computation. So for that reason we are making use of this one.
Right. Thank you.
Thank you, sir.
Dr. Sharma, any questions for our speaker?
First of all, nice presentation, Kavita.
Thank you, sir.
My question is that what evaluation matrices you use?
Here, sir. Mainly accuracy, sir.
No, what evaluation matrices you use? I think you use kappa.
Coefficient and
Kappa.
okay.
Yeah,
Ha,
yeah,
ha,
yeah.
ha. Yes, sir.
Uh, Second question is that how you handle high dimensionality in high spectral data?
Yes, sir. So that is the disadvantage with the hyperspectral images. But this high dimensionality data, we are making use of the selection of the features, only the major feature, wherein we are concentrating on having the spectral features as well as the spatial context, whichever are important, are only those features we are extracting and then we are fusing. So in the second layer itself only we are going for the parallel operation, and in the parallel operation we are separating and then we are combining whichever are important. So in that way, in the second layer only we are reducing on the number of the features, and in this way we are handling the high dimensional data. But even if comparatively the number of the data whatever we are considering, it is very much lesser compared to the normal data, because this spectral data, it is going to occupy lot of the size. So for that reason, I cannot have lakhs of the data. I can have only hundreds of the data or tens of the data. I cannot have lakhs of the data or millions of the data. For that, computationally doing computational computing is very difficult.
Thank you. Thank you.
Thank you so much for your presentation, ma'am.
Thank you, sir. Thank you so much for giving the
We now
opportunity.
move on to the next presentation. The next presentation will be done by Anisha Panja from the Kalinga Institute of Industrial Technology in India, and the title of the research paper is Robust and Interpretable Credit Card Fraud Detection, a systematic evaluation of machine learning models under severe class imbalance. Ma'am, I request you to kindly unmute yourself and start presenting, please.
Yes, sir. Yes, I'll present it. So, is it visible?
Yes, your screen is visible and you are audible as well, so you can
Okay.
start.
So, good afternoon, respected session chairs, distinguished professors, and fellow researchers. I am Anisha Panja from School of Computer Engineering, deemed to be University Bhubaneswar, India. And today I'll be presenting our work titled Robust and Interpretable Credit Card Fraud Detection, which is basically a systematic evaluation of machine learning models under severe class imbalance. So, our work focuses on a very practical challenge in financial systems: how to reliably detect rare fraudulent transactions without actually overwhelming the system with false alarms. So, to begin with the domain context, credit card fraud refers to unauthorized or deceptive transactions performed using stolen credentials or compromised identities. And with the rapid growth of digital payments, online banking, and e commerce systems, the volume of transactions online has increased massively, making the manual fraud detection monitoring nearly impossible. So, this is why machine learning based fraud detection systems are widely used today. However, fraud patterns today in today's world are often subtle, adaptive, and intentionally disguised, which makes reliable detection of highly challenging machine learning problems. Now, coming to the core challenge, the central challenge addressed in our work is extreme class imbalance. For the dataset we have used, it consists of 284,807 total transactions, and out of which only 492 are fraud transactions, which is approximately only 0.17% of the total. And as you can see in the figure, this creates a highly skewed distribution where legitimate transactions overwhelmingly dominate the data. Under such conditions, the model may tend to become biased towards the majority class, that is the legitimate transactions, and may ignore the minority fraud cases entirely. So the visualization clearly highlights how rare fraud events are compared to normal transactions in real life. So why traditional evaluation fails is that under severe class imbalance, traditional evaluation matrices such as accuracy becomes misleading. So what I mean by that is, let us suppose if a model predicts every transaction as legitimate, it can still achieve almost more than 99% accuracy while completely failing to detect any fraud. So despite a strong numerical accuracy, which is generally favorable for the eyes, but the model is practically useless because it fails to detect any fraud, which is our main motive. So this motivates the use of imbalance-aware matrices that truly captures minority class performance. Now, while doing the literature survey, we found that existing literature in fraud detection often emphasizes complex architectures such as deep learning models and focuses heavily on improving accuracy or ROCAOC. However, there is a very relatively limited focus on how standard machine learning models behave under real severe imbalance without any synthetic resampling, especially in terms of precision recall trade-offs and deployment practicability. So this motivated our study, and instead of proposing any new algorithm, we aimed to perform a systematic and metric-aware evaluation of representative models under realistic data conditions. The primary objective of our study is to compare standard machine learning models under severe class imbalance and identify which model offers the best operational balance. And we specifically focused on fraud detection capability, false positive burden, interpretability, and computational feasibility. The broader goal is to derive insights that are more suitable for real-world deployment scenarios. Now, coming to the methodology of our work, the dataset is first divided into a stratified 80-20 testing and training split, which preserves the original fraud ratio in both the subjects. We haven't applied any synthetic resampling techniques because our goal is to retrain and retain the original real-world data characteristics. We have used 3 representative models in our work. As you can see, they are logistic regression as a linear baseline, random forest as a bagging-based ensemble, and XGBoost as a boosting-based ensemble. And all the models have been trained under the same consistent setup to ensure fairness and reproducibility. So this workflow in the right, as you can see, summarizes the entire pipeline followed in our study. Now, coming to the evaluation matrices that we have used, since the dataset that we have used is highly imbalanced, we use machine learning matrices that better reflect minority class behavior. This includes precision, recall, F1 score, PR, AUC, and MCC. Accuracy in our work is intentionally excluded as a primary metric because it fails to capture fraud detection quality in some settings where fraud is really in very less number in the data. Now, coming to the results and key insights, the comparative results show that random forest, which is a bagging-based ensemble model, achieves the best overall performance in our study. It maintains both high precision and strong recall, which indicates that it successfully captures fraud patterns while keeping false positive under control. XGBoost, which is a boosting-based ensemble method, also performs competitively, but slightly lower than random forest in our setup. Logistic regression, being linear, shows reduced recall and misses a large number of fraud cases. This suggests that nonlinear ensemble-based methods like random forest and XGBoost are more robust in this problem setting. And as you can see in the table, random forest consistently performs and provides the best balance across the key matrices like the trade-off, precision, recall. Now, one of the most important insights in this study is the trade-off between fraud detection and false positive. So increasing recall helps capture more fraud transaction, which is usually good, but it also increases the number of false alerts. And in the real financial system, this creates operational cost in terms of manual verification effort, customer dissatisfaction, and blocked legitimate transaction. Therefore, the true goal in our study is not to maximize a single matrix, but to identify a balanced operating region that actually minimizes both missed fraud and unnecessary false alarms. This slide visually summarizes the balance between all the models. Now, in conclusion, this study demonstrates that ensemble-based models, particularly random forest, are more robust under severe class imbalance. The work also highlights the importance of using PRAUC, that is precision recall area under curve, and MCC, that is Matthews correlation coefficient, instead of misleading accuracy-based evaluation. More importantly, the study emphasizes the operational trade-offs must be considered along with model performance and shouldn't be only focusing on the performance of the model. As a future work, the framework can be extended towards real-time fraud monitoring system, lightweight deployment pipelines, and adaptive threshold optimization. Thank you for your time and attention, and I would like to take any suggestions and questions ahead.
Thank you so much for your presentation, ma'am. Dr.
Thank you so
Tauhid,
much.
any questions for her?
Sure. Thank you. Thank you for your talk here. I appreciate your talk today.
Thanks.
So my question here, you have how many data sets you have? You have only one data set. You are applying this three classification here.
Yes.
Three
Yes, sir.
classifier, one data set.
Yes, sir. We have used just one data set. It's a publicly
Yes.
available data set, and it
So-
consists of total transactions that are 284,807. And in this data set, it is actually a real data set. And only 492 of these total value are only fraud, and the rest are legitimate transactions.
Yes. So I was hoping that if you apply your approach here for more than few data sets, more than
Yes.
one, so
Yes,
that
sir.
you can see, because for your work, you see random forest may be the best for this specific data set. But if
Yes.
you apply, if you have say 5 data set or 10, we would like to see which classifier will be overall is the best.
Yes, I do understand that. Maybe random forest is acting as bias towards this data set and it may perform differently for the other data sets.
Yes. Thank
Yes.
you.
Thank you so much, sir.
Dr. Sharma, any questions?
Hello.
Yes, sir.
Hi, sir.
My question is that what are the key findings of your systematic evaluation regarding robustness and model performance?
Sir, in this work, we didn't mean to create any complex architecture, rather a systematic evaluation where we wanted to show that like in most of the studies we use matrices like accuracy as a major metrics that we judge the model on. But in case of fraud detection in today's world, it is like one of the important domains. So here accuracy may be just, I mean, not accuracy, but only accuracy may be misleading because like if we want to take an example in another domain, like in airport, if a security checks and there are a lot of passengers, so even if the security checks all the legitimate the unharming passengers as correctly, so he will if he's a model, he will perform 99% accuracy, and if he fails to detect or catch only maybe two of the risky persons, then also he will get a 99% accuracy. So that is the thing, that he misses actually the important risky persons, but he also at the same time he gets accuracy which is even more than 99%. So in this model we wanted to show that only accuracy is deceptive, rather we should focus on precision and recall so that we can understand that what is the fraud detecting capability of the model, and at the same time we want to reduce the false positive alarms because it creates unnecessary alarms for legitimate customers, and it creates problem for them.
Any limitation of your work?
Sir, like this is a base work I have started, so looking forward to carry it out on further basis using maybe other data sets, other models, and including any other feature extraction techniques maybe, or pre-processing.
Okay, thank you.
Thank you so much, sir.
Thank you so much for your presentation, ma'am.
Thank you so much.
Yeah, sure. I would once again like to confirm we had one of our speakers who is present in the meeting, but when the name was called out, they couldn't respond. Mr. Uh, M. Sudhakar, I believe. Yes, Mr. M. Sudhakar, can you hear me?
Hello, sir. This is
Yes,
Srivan
ma'am.
from Sudhakar stream, sir. Am I audible, sir?
Yes, ma'am, you are audible.
So, can I start the presentation, sir?
Okay, are you one of the co-authors for Mr. M.
Yes, sir.
Sudhakar?
I'm one of the team members.
Oh, sure, you can start presenting, ma'am.
Yeah, thank you for the opportunity, sir. Good afternoon to respected session chairs and all the participants. This is Srivani, and I'm a final year undergraduate student in the computer science. Today, I'm presenting a paper titled Edge-Enabled Federated Learning for Privacy Preserving Healthcare Analytics.
Excuse me, ma'am.
Can you
Yes, sir.
show screen?
Are you sharing any presentation because we can't see anything?
Yes, yes. Is my screen is visible, sir?
Yes, ma'am, it's visible. You can continue.
Yeah. Thank you so much for the confirmation, sir. Today I'm presenting a paper titled Edge-Enabled Federated Learning for Privacy Preserving and Healthcare Analytics. This work was done in the collaboration with my team members, Sudhakar and followed by Surya Praveen. We are from Lucky Reddy Balreddy College of Engineering, India. Now I'll briefly explain about our. So let me start with the even by trusting them. So traditional machine learning requires centralized data, which leads to the privacy. So to solve this, our project uses federated learning with edge computing, where multiple devices like hospitals and wearables train models locally, and only model updates will be shared, not the actual patient data that we'll be having. So if we do this particular process, we are going to ensure that privacy protection, reduce latency means we'll be getting the fast updates rather than the latency, and also efficient healthcare analytics. This is about the abstraction. Now coming to the introduction. So here our system allows multiple healthcare devices to collaboratively train the models without sharing any of the raw data that we have. So here we are using the edge devices like hospital processes data locally, and also the encrypted updates are sent to the server. So if we do this particular process, we are going to improve the security, efficiency, and also the real time monitoring. And these are the benefits of our project that we are going to work with. Now coming to the literature survey, so here we have researched many papers. So among this we have selected only the few particular papers in federated learning in the healthcare. So on overall key observations, what we have observed is federated learning protects the privacy, enables collaboration between the hospitals, which improves the accuracy. However, existing systems face many challenges like communication delay, complexity, and also the scalability issues. So these are the main drawbacks that we are going to observe in the research papers. Now, I want to say the existing drawbacks. So existing system have several limitations. Limitations in the sense like drawbacks. So risk of data leakage. This is one of the major disadvantages. Poor scalability means we are unable to scale up and down the resources, and also poor scalability, low reliability, and also lack of proper frameworks that we have now. These are the existing drawbacks. Now by removing all these things, so we are going to develop a particular project. Means merits of our project. Our project overcomes these problems by ensuring no raw data sharing, using edge computing for fast processing, supporting scalability, providing real-time monitoring dashboard. These are the merits of our particular project. Now, what is the system that we are going to propose is, our proposed system uses the edge-enabled federated learning. So each hospital or the devices process the data locally. Trains a model. Then sends only the model parameters, like server is going to combine them using the federated averaging. This results in a global model that improves the accuracy while maintaining the privacy. Now coming to the tech stack, we use the following technologies for Python for development. Now the TensorFlow and Keras for deep learning, and federated learning for the distributed training, edge computing for local preprocessing, NumPy and Pandas, as we know, for data handling we are going to use, and especially we are familiar with the Streamlit and the Matplotlib for the visualization purposes, and encryption technique for secure communication, means we cannot able to see the actual data whenever we are going to transfer our data to the third party or other people. So in order to hide our actual data, we are going to use like encryption techniques. Now the flow graph is like, this diagram shows the workflow. Actually the data is collected at the hospitals, at the primary, like edge devices, hospitals, or variables, or from the clinics. So the data is processed locally, pre-processed locally. Only the local models are trained. Model parameters are sent securely, and the server aggregates them. This ensures the learning without data sharing. This is like flow of architecture. Is going to pre-processing, and local training is going to happen. So in the encrypted updates, only server is going to aggregate all those things. So this process is going to repeat for multiple rounds, and also so that it ensures that we are going to get a good accuracy. Okay, that is the reason why we are going to take the rounds. So in our project, we are going to take the 5 rounds in order to improve the accuracy of a particular project. Now, the flow of architecture, I'm going to explain. Like edge devices includes hospitals or the variables, central server, and also the secure communication. It shows like how distributed learning happens without compromising the privacy. This is like flow of architecture. See in the diagrammatic representation. So we are going to collect the data from edge devices like hospitals database, hospital data, wearable data, and also from the clinics. So in the local model training, we are going to use like CNN, gradient boosting, these things here. The CNN is like convolutional neural network, which is a deep learning model used for like image processing. And also coming to next one, which is gradient boosting. It is like used in the federated learning, which is going to correct the errors that we have in our model, and used for improving the accuracy. And next one is the SVC. It is like used for classification purposes, and it is going to separate the different classes. And next I've explained about the encryption model updates. So we are going to pre-process all these things, the data that we have, and it is going to send to the central server. So only the model updates will be stored into the fed averaging and stored in the global updates. And finally we are going to show all these things through the dashboard that we are going to use, like using the Streamlit, which is like used for the visualization representation. And finally we are going to predict whether that particular person is going to attack with the disease or not, like patient monitoring. We are going to check all those things in the flow of architecture. See here, if you observe the results, we have taken many parameters. The one thing that we should able to remember is the disease will not be able to judge or the determine only one particular aspect. It could be depends on many parameters of the aspects like resting blood pressure, and also the cholesterol, max heartbeat rate. If the blood pressure is high, we cannot able to decide that that particular person is suffering with the heart disease. So it may depends on many things. So for this person, there is no heart disease, saying like there is a normal heart because all the parameters are in normal. So in the coming to the next one, it is showing like heart disease because here the resting blood pressure is 170 and also suffering with the severe chest pain, and cholesterol is like 199.
Excuse me, ma'am.
So these are the results, sir.
Just a reminder, you have 2 more minutes left. Thank you.
Yeah, thank you. Okay. And next, and this is like diabetes disease detection. Sir, is my screen is visible or stuck anywhere else? Right?
I think the conclusion and the diabetes detection is visible.
Yeah. Yes, sir.
But it's not visible fully. There is
Yes, sir. That's
kind of
what
an
I've
obstruction.
just asked. I think network issue. That's what I'm unable to show. Yeah, no worries. Even I can explain. So
Sure.
now coming to the next one, diabetes disease detection. So as I said earlier, the even any particular disease will not be determined only on one particular aspect. As I said earlier, so here it is showing like normal. Um, we have parameters like body mass index, BMI, which is BMI, and plasma glucose concentration, showing like 9.70, here 38.20. All this value shows like it is normal. And coming to here, since the values are very high, so it obviously going to show he is suffering with the diabetes. So in our project, we have used only two things, like whether that particular person is normal or suffering with that particular disease. Only two, like binary 1 and 0. Now finally, our coming to the conclusion, our project provides a secure and scalable healthcare analytics system using the federated learning and edge computing. So finally, what we are going to ensure like privacy, efficiency, and real-time monitoring, and supports the application like a disease prediction. So I'm done with my presentations.
Okay, thank you, ma'am. I now ask Dr. Tauhid, any questions for our speaker?
No, thank you. Thank you. It's a nice presentation. Thank you. I don't have questions.
Okay, Dr. Sharma?
Nice presentation, Arugula. Tell me what type of healthcare data you use in your system?
So actually, we have used three types of healthcare data, sir, like heart disease, diabetes, and liver-related things. Like, show. Yes, heart disease detection, liver, and diabetes. Yeah, these three things we have used.
Okay, thank you.
Sir.
Any more questions for our speaker?
Thank you.
Okay.
Thank you, sir.
We have one last presentation left, which it was supposed to be done in one of the previous sessions, but they weren't available, so we can do it right now. So the title of the research paper is Driver Drowsiness Detection Using YOLO V5, CNN, and LSTM. And the co-author who will be presenting is Spurgeon Vadapalli. I apologize for any mispronunciations. But sir, you can start presenting, please. Thank you.
Yes, sir. Thank you.
Sir, are you able to share your screen?
Yes, sir. I'm sharing.
Oh, okay.
Is it visible, sir? Hello, is it visible, sir?
Yes, sir, it's visible. You can start.
Okay, good morning, respected chairpersons and everyone present here. This is Spurgeon. and today I am presenting our project titled Driver Drowsiness Detection using deep learning models like YOLO V5, CNN, and LSTM. So coming to the abstract of our project, the main problem nowadays we're facing is road accidents due to driver drowsiness are a major global issue. Fatigue reduces reaction time and increases the risk of accidents. Our project aims to develop a real-time system that detects driver drowsiness and alerts them to prevent accidents. So we have done a literature survey about so many papers, and we are presenting just 2 to 3. These are the okay. These existing systems for driver drowsiness detection have several limitations. They are not accurate in real-time conditions, and they fail under different lighting conditions. And many systems cannot handle the facial variations like spectacles, and some require wearable devices which are not convenient. Hence, there is a need for efficient and non-intrusive and real-time solution. So, these are all the existed system architectures which fail in these aspects, like real-time conditions and different lighting conditions. So we propose a new system which uses YOLO V5 for real-time face and eye detection and CNN for feature extraction, and uses LSTM to analyze temporal patterns of eye closure. Our system continuously monitors the driver's face through a camera and detects the sign of drowsiness such as eye closure, blink rate, head movement, and yawnings also. If driver drowsiness is detected, an alarm is generated immediately. So this is our architecture. The data acquisition will be done by camera and feature extraction and the pre-processing step done by YOLA V5, which detects the face and eyes and mouth uh, of the person, and feature extraction is done by CNN, and LSTM is used to classify the drowsiness and the length of the mouth and eyes, etc. So the first one is data collection. We collect images, video data of drivers in different conditions. Pre-processing steps include noise removal, image resizing, and normalization, and detection using YOLA V5. YOLA V5 generally detects the face, eyes of the person. It provides the bounding boxes in real time. And the feature extraction will be done by CNN. It extracts important features such as eye openness and facial patterns, etc. Temporal analysis using LSTM. Uh, it analyzes sequences over time, like continuous eye closure, blinking duration, and the length of the yawning. So if any drowsiness is detected, so immediately alarm is triggered and driver is alerted instantly. So this is the implementation of ours, and we used one data set which is about 42,000 entries in it, and these are the results of our project. This is how the eyes and mouth is detected. This is the yawnings. Euclidean distance is used to measure the distance. So our system achieved high accuracy in detecting drowsiness, real-time performance, robust detection, even with spectacles and lightning variations. This shows that our model is efficient and reliable for practical use. In conclusion, our system successfully detects driver drowsiness in real time. It reduces accident risk, and it is non-intrusive and easy to use. This makes it suitable for real-world applications in vehicles. In future, if we can improve accuracy using larger data sets, integrate with IoT for vehicle control, and adds features like yawning detection mode, and deploy it in smart vehicles, that would be great use for the society. And yeah, yes, sir. Thank you for this. Thank you for your time. I'm happy to answer any questions.
Okay, thank you so much, sir. Dr. Tawhid, any questions?
Yes, thank you. Thank you for the presentation here. So you give us a review for literatures here. So when you start the first few slides here, so did you compare your approach here with this other approach that you mentioned at the beginning?
Yes, sir. Others uses more CNN and LSTM for their projects, but what what we think is they are not that much suitable for real world application, which is happening at the present. So Yola V5 detects faster than those proposed systems, I think.
I see. How big the data set that you have?
So it's about 42,000 entries.
It's only one data set?
Yes, sir. It's only one data set.
Okay, thank you.
Thank you, sir.
Dr. Sharma, any questions?
Oh, nice presentation. How you remove noise?
Thank you. Sir, noise can be removed by data augmentation and normalization and data cleaning.
What do you use here? What do you use here? All these and someone.
Sir, many data augmentation, sir. We gather different types of data uh, so we can overcome the issue of noise.
Okay, thank you.
Thank you, sir.
Okay, thank you so much for your presentation, sir. We
Thank you,
have
sir.
one last presentation lined up for today. So this presentation will be done by B. Mathura from the Vallurupalli Nageswara Rao Vijnana Jyoti Institute of Engineering and Technology in India. And the title of the research paper is Federated Learning and Multimodal Federated Learning, a review in healthcare domain. Ma'am, I request you to kindly start presenting, please.
Yes, sir. Good afternoon, one and all who are there present here virtually. First, let me share my screen, sir. Sir, is my screen visible, sir?
Yes, ma'am, it's visible. You can start.
Yeah. Yes, sir. So, good afternoon once again for all the participants who are there in this virtual room and the reviewers. So, I'm being presenting this paper as part of the 11th International Conference, that is ICTIS 2026. The paper ID is 1408, Federated Learning and Multimodal Federated Learning, a review in the health domain. So proceeding, the agenda of this presentation would be, first I would like to briefly introduce about the introduction part of it, then followed by it a federated learning system and the usage of it in the medical healthcare, the advantages of it, the challenges which we encountered, and where one of the challenges been overcome using multimodal federated learning, and the challenges which we encountered, followed by it are references. So starting with the first agenda part, that is introduction. So we are trying to build an AI intelligent systems where we need large amount of medical data for the analysis, and these intelligent systems should be handling such huge amount of data as well, and they should also adapt to the dynamic environments. Like if I use an IoT device, it has to adapt accordingly for that, and so on. So an investigation which is held with a huge amount of medical data, it was a challenge. Why? Because it is distributed among multiple institutions like hospitals, healthcare centers, and everything. So collection of all such data at a central point is becomes a challenge. Why? Because we do have some medical data policy constraints for each of the units there. So the collaborative learning methods where we apply the deep learning, machine learning methods, they all rely on the centralization of the private and sensitive data, which uses institutional incremental learning policies, and then perform the analysis part on it, for which we can use it for the disease prediction and identification of the disease and so on. So but this was found to be a complex. Why? Because main concern is about the private data, the security of aspects of the patient sensible data. So when the solution for that was found to be a federated learning mechanism. So the federated learning is a framework which enables a distributed learning of the models of the on the medical data sets which were remotely hosted. So we do have something like a client server architecture where the clients will be having a local models where they consider the local sensitive data, patient data, use it and develop a model. And this model, along with the hyperparameters, will be transferred to a central point of a server. So this aggregation is done at the server side. So federated learning allows extensive aggregation of the diverse databases from different health centers, and perform the aggregation and then provide the analysis part of it as a part of a report generation. So federated machine learning mechanisms use a centralized medical data computation, maintaining the medical data as well as the user privacy. So if we get just according to this federated learning system mechanism, so as I told you, this is a client server based mechanism, where in the client level we have different centers, remote centers, wherein we perform private or sensible data analysis done at there with the help of a local models, and these local models along with the prerequisite hyperparameters only is being shared to the server. So thus we are securing the patient level sensible data there. And at the server level, we do have some learning systems wherein we will aggregate all them with different aggregation methods, different fusion methods and so on. Then we will test this as a global model, and then you can optimize it and later deploy it for a large scale systems, so that it can perform the federated learning mechanism as a centralized component, maintaining the security main. So this federated learning usage for the medical data, when it is used for identifying different diseases like cancer detection, brain tumor, skin disease, COVID, thyroid, heart disease, and the list is endless actually. Now, coming down to the advantages of it, federated learning advantages mainly includes the local training, which will have a high autonomy, maintaining the privacy or sensible, maintaining the securing the data, private data, the decentralized system, which are or which have accelerated training models, and these models, instead of sharing the models, only the parameters of these models are being forwarded to the server, therein reducing the data management and the IoT enabled AI sensors and everything. The deployment of all such resources also reduced here, since they are at the local endpoint. So next, it also involves minimal data labeling and the network outsourcing as well. So the communication devices which we have, it will be also less, and these are mainly used for a huge projects where we have most of the crowdsourcing, a huge amount of information to be analyzed. The challenges which we encountered in this federated learning starts with your privacy and security concerns. So wherein, if while we are sharing the hyperparameters as well, in case if we lose any sensible data, then how do we handle it? That can be also one of the challenge in the federated learning. The number of clients, how many clients you'll connected, the system heterogeneity, the number of clients which we connect, and with the different types of data, that we call it as a data heterogeneity, the initialization and the synchronization. Since we are doing aggregation, how do we start up, how do we synchronize with the clients, the communication overhead, it's an additional part. Why? Because we are doing it not at a single point, we will connect it with multiple clients. The resource allocation, the imbalance of the data, mostly in the healthcare sectors we do have the data which where we'll have patients data more than the patients without any disease data less. So scalability of the disease. Now, one of the challenge in these federated learning, that is data heterogeneity, is being handled with the next concept, that is multimodal federated learning. So multimodal federated learning is integrates complex multiple modalities, where federated learning will be handling with only one type of modality. Usually we call it as a unimodal. They do analysis only through that one particular type of data, which can be either a text data or it can be something like an image data. Whereas when we go for multimodal federated learning, we will be handling multiple modalities, providing a more holistic, richer understanding of the data in the decentralized system. Multimodal federated learning involves collaborative training of the multiple models distributed across multiple clients. Since we are doing an integration, collaborative learning here with these different federated learning systems, so here we will have across the multiple clients. And federated learning system handles predominantly unimodal, whereas when we go for this multimodal, we will be handling with multiple models, like with the different environments like wireless applications, IoT, edge devices, sensor input, image, audio, and text. which can be shown in this diagram here. So in the multimodal federated learning, we are not concentrating only to one type of modality. We do involve medical images, genomic sequence. It can be a variable device with all different types of sensors, or it can be an healthcare data in the form of an electronic health record, or it can be a textual data or a database or a tabular form of data. Now, proceeding further, the advantage of this multimodal federated learning is in the case of a uni model, each modality will have a separate federated learning system. So it's something like for a particular image, we'll have one federated learning system. For the textual, for the edge devices, we'll have one. For the textual data, we'll have one federated learning systems. But when we come down to the multimodal federated learning, we can have a centralized one, a collaborative one, where we will combine all these different modalities together for that single multimodal federated learning system. So this can be considered as a major application or a major advantages of the multimodal federated learning. Now, coming to the challenges of it, the challenges which we identified for this multimodal federated learning is, one is the model heterogeneity. Since we are handling with multiple modalities, the distribution gaps between the multiple modalities has to be handled. This can be one of the challenge which we have identified in
Excuse me,
this
ma'am.
review. Sir.
Just a reminder, you have 2 more minutes left.
Yes, sir.
Thank you.
And the other one is a modality imbalance and the missing modalities. When we try to do multiple modalities combination, we may miss up with some textual data, or we may miss up with some image data. So when we are doing analysis, we have to compensate it or do imputation for that. So that can be one possible challenge. And the other one is the fusion complexity. Since we are having multiple modalities to be combined, the way of fusion which we do, it can be simple combination, or it can be a simple addition or a concatenation. So all the different fusion complexity is involved in the case of this multimodal federated learning. So these are few of the challenges which we have identified in the review, sir. So concluding this, we started up with the federated learning, application of it in the medical healthcare, and one of the challenge of the federated learning, that is handling data heterogeneity, which can be resolved using multimodal federated learning. And when we implement such a system, the challenges identified as this, which can be reviewed for the which can be considered for the next future research. This is the conclusion of my presentation, sir. Uh, thank you, and if any queries.
Thank you so much, ma'am.
Yeah.
Dr. Tawhid, any questions for our speaker?
Sure. Thank you for your presentation. I really appreciate it here. So how you do the optimization that you mentioned in your diagram that you have? You said at the end you do the optimization. How you do it?
Yes, the optimization can be with respect to, if I consider a federated learning system where I'll take different data from different clients from the different sectors. So after I collect and get the hyperparameters, I'll combine them, and after combining, the way of fusion is done or the combination is done. If the combination leads to the better way of presenting the disease or identifying the disease, then if that is finalized, then we can end up, or else we will change the parameters which we collected from the client side, sir, so that we can optimize and get a global model there.
All right, thank you.
Yeah.
Dr. Sharma, any questions?
First of all, nice presentation, Dr. Mathura. Hello. Hello.
You
Sir.
are audible, sir.
Question is that what are the common aggregation technique used in FL?
The common aggregation techniques
Yes.
used in federated learning, sir?
Yeah.
Generally, we have different aggregation techniques, like a simple combination, like combining them unit wise, or it can be something like based on the priority. The sector which has got a prominence more can be given more weightage, like weighted form, or it can be something like based on the data which is available, the importance of the data which is available in that particular sector. So these can be some of the possible aggregation methods.
Any evaluation matrices you use in FL or ML?
So the evaluation measures will be the same as your normal measures which we use for the intelligent systems like ML and DL models. It can be either an accuracy or a confusion matrix or the precision recall and so on, sir.
Thank you. Thank you. Thank you.
Yes.
Okay, thank you so much for your presentation, ma'am.
Thank you, sir.
So that brings us to the end of session 9F. I now request Dr. Mohammed Tawhid to give us his closing remarks.
Sir, am I audible?
Yes, sir, you are audible.
Sir, I am here to present my paper.
You had to present?
My paper, sir. This is my batch, sir.
Oh, okay. I'm so sorry. We can take your presentation as well.
Okay, sir.
Yeah, Mukh, even mine as well.
Okay, sir, we can do that as well. Give me just a second.
Sir, shall I present?
Yes, sir, you can start presenting, please.
Sir, thank you, sir. Good afternoon to one and all.
Excuse me, sir. Can you please pause for a second? We can.
Sir, am I audible?
Yes, sir, you are audible, but can we do your presentation later? We need to do Mr. Mohammed Mudassir's presentation first.
Okay, sir. Okay, sir. No
After that, you can continue.
Sure,
I'm so
sir.
sorry. Yeah. Mr. Mudassir, you can start
Yes,
presenting, please.
thank you. Let me share my screen. Is my screen visible?
Yes, sir, your screen is visible.
Okay, so hello everyone. Now, before I explain what my project or paper is all about, I'd like to talk about what problem I'm trying to solve. And instead of going through slides, I'll actually show a demo where I have developed. So let's talk about the problem. So basically, there are 3D models which are being circulated. Like there are many artists where they build a 3D model and they're distributed in certain platforms. So for example, there's a platform called Sketchfab where all the 3D models are being like distributed. But the main problem of this is the piracy. Like many artists, they develop the model and someone else copies it or downloads it without their permission. Once they buy it, and after that, they resell it using their own name. And there is no central authority which would verify this, like who the real artist is. So, in order to solve, what if there was a platform where the artist can register themselves? So, this would act like a central authority which will keep the record of all the artists. So, for example, if I'm a 3D artist, I'm going to register in this platform. I'll get the verification and everything. And there's a certain marketplace where I can upload my 3D models. But before uploading, I'm going to sign this model using my credentials. And it's going to generate a manifest file, which is like a certificate. It's going to get embedded with the 3D model. So anyone can verify who the real artist is. So for example, let me upload a 3D model. So this is the model which was created and we can see the preview. I'll just generate a fingerprint and it's going to sign it. So behind the scenes, what's happening is it's going to bundle, generate a hash and bundle it with the 3D model. And it's using steganography and as well as normalization. I'm going to download this. So this is a sign model. And if I want to verify, I'll just upload this in the section. So anyone can verify like who the real artist is. And it will show all the signed details and everything. Now, suppose someone else downloads it and they want going to sign it, this model with their own credentials, but the platform won't let it happen. So I'll again upload the same model. So it won't let me sign it again because the hash map has been saved into our central registry, so it knows who the real artist is. So this is how we can solve the problem of piracy and who the real author is. So where the artist can sell their products, 3D models in this platform. This was the presentation and demo. Any questions or doubts?
Dr. Tawhid, any questions for our speaker?
No, thank you.
Okay.
Dr.
Thank
Sharma?
you.
Question is that how does your system detect and localize tampering within the 3D model data?
Okay. So basically, while generating the signature, right, we have the public and the private key. So while generating it, we extract the 3D model and it's going to calculate the coordinates and everything. Like when we extract the 3D model, it has all the vertices. which is going to extract and create a hash map. So by that, we'll be able to store it in the platform. So if someone else tries to upload the same model, so our system is going to detect it because the hash it's going to match, right? So that's how it
Okay,
is.
thank you. Thank you.
Thank you.
Thank you so much for your presentation, sir. I'm sorry I missed your message in the chat.
That's fine.
Our next presentation is going to be done by P. Saravana Gukhan. Sir, you can start presenting, please.
Thank you, sir. Thank you. Good afternoon, one and all. Sir, I'd like to share my screen first. Shall I share my screen, sir?
Sure, sir, you can do it.
So, my screen is visible now.
Yes, sir, your screen is now visible. You can start, please.
Sir, is my screen is visible?
Yes, sir, it is visible.
One second, sir. Thank you, sir. Thank you, sir. So, I'd like to introduce myself. I am P. Saravana, pursuing final year student of ADS department in Dr. Mahalingam College of Engineering and Technology, India. This is my project based on a title, a robust deep learning framework for automated diabetic retinopathy detection and severity grading. The
Excuse me,
ambition
sir.
of the sir.
Actually, your voice is a little bit low. If you can speak up, it would be better, please.
Okay, sir. Okay, sir. No problem.
Okay, thank you. Sorry to interrupt.
Okay, sir. So is that clear? Am I audible?
Yes, now it's better.
Okay, sir. Thank you, sir. So, my paper on a title, a robust deep learning framework for automated diabetic retinopathy detection and severity grading. The ambition of the project is to detect the retinal fungus disease in our eye, that to detect in the early stage and detect in a way that propose the severity grading, mild, severe, high, mid, that like, sir. Let's go with the introduction, sir. The introduction, diabetic retinopathy, it currently faces several challenges in clinical practice. That work focuses on addressing these key limitations using an automated deep learning framework, sir.
Excuse me, sir.
Sir.
Sorry to interrupt again, but the Zoom window is actually coming up in front of your presentation. If you can close it, please. Or you can move it to the side. That's
So,
fine as well.
okay,
Yes,
sir.
now it's visible. You can continue.
Okay,
Sorry.
sir. Thank you, sir. So let's go with the introduction. Sorry, sir. Sorry for the interruption, sir. Some issues in the laptop, sir. Sorry. So let's see the introduction. Diabetic retinopathy (DR) is currently faces several challenges in clinical practices. The early proposed systems are not proposed very accurate grading of the disease, sir. The work focuses on addressing these key limitations using an automated deep learning framework, sir. We use the deep learning frameworks like TensorFlow, Keras, that's like, sir. And its manual diagnosis may vary between experts, leading to inconsistent results. An automated model helps provide more consistent and accurate predictions. Motivation of the study is to develop an automated and a reliable detection system that reduces overload of healthcare professionals. So it's audible, clear? Hello, sir?
Audible.
Thank you, sir. So the literature review, the literature review says, uh, one second, sir, sorry, sir. Sir, this diabetic retinopathy detection currently faces its traditional diagnosis depends heavily on ophthalmologists, which makes the screening process time-consuming and more expensive. But this proposed system introduces automated detection using deep learning, reducing manual workload. So the diagnosis may it's this project uses in many rural areas and remote areas. It's very helpful in the rural areas, sir. Just 1 second, sir. So the problem domain, sir. Problem domain. It's screening manual dependency, automated system, traditional diagnosis relies on ophthalmology, sir. So get a little bit nervous, sir. Sorry, sir.
Sir, are you facing any problem?
Sir, sir, I'm audible?
Yeah,
Yes, you are
audible.
audible and your screen is visible as well.
Okay, sir. So sorry for the interruption, sir. Let's start with the literature review, sir. So shall I proceed?
Next. Yes.
Sure, sir.
Okay, sir. So this diabetic retinopathy, it what to say? So our proposed system introduced automated detection, sir. We use a deep learning framework like TensorFlow and Keras. We have a data set of 35,000 images that that shows how severity the retinal will damage, and we get the patient's images also, and we compare the both our data sets and the photos of the patients, and our app gets the result by severity grading. It's mild, over, or severity, or profile rate, something like that, so that we this uses manual screening dependency, human error and variability. It fits human error and variability, and it's give results in a expert level, uh, and in a few seconds it's give results and with the accuracy of the retinal damage. It fits the delay results comparing to proposed system, and we I'm sorry. And the image quality also, as well as improve the images of the retinal image. It's by using data pre-processing, data cleaning, we remove the noise of the picture, lighting of the picture, and its proposed quality variation of the results, sir. Then move to the methodology, sir. In methodology, we have image acquisition. The system utilizes images of the retinal fundus obtained from publicly available diabetic retinopathy data, such that which is contain multiple examples of all levels of severity, from normal, mild, moderate, severe to profiled retinopathy. All of these images contained within these databases were obtained controlled clinical conditions and high quality color fungus images. This only I says before that we have 35,000 images in our data set, and this is the method to image get a photo of our patient's eye, and we had to compare the both images, and we propose the severity grading. Image pre-processing. The necessity of this image pre-processing. Pre-processing should enhance diagnostic relevance and create a standardized level of quality in the images. We use a CNN to develop consistent dimensionality, pixel insulation normalization, It is used to reduce variance due to the use of different capture equipment and lightning conditions also. And next one is future extraction. Future extraction using by conventional neural networks, that is CNN, which is future extraction is performed using a CNN design. Its layers use multiple learnable kernel to process the pre-processed images and create future maps uh, that that capture spatial hierarchy of futures in the images, which highly conventional feature maps capture low-level features like edges and textures. The deeper conventional layers capture complex lesion-specific patterns associated with the progression of the disease. This is experimental setup, sir. CAG diabetic retinopathy detection dataset. This is the dataset we have in our files. Number of images is 35,000 retinal fundus images we have. Classes, this is no DR. No DR means if there is no retinopathy disease, it result in a no DR. Mild means mild, moderate means moderate, severe means severe, profilate means profilate, sir. And we use as Python frameworks like TensorFlow, Keras, libraries like OpenCV, NumPy, Pandas, and a platform like Google Colab, Jupyter Notebooks. Sir. This is the results and discussions that we shows in the tabular column, sir. Data used, ID or ID data set, descriptions that public retinal fundus image with expert D or severity labels. And the image size is also 2224 into 224 pixels. And training testing splits through 80% to 20%, which is data set divided for model learning and evaluation.
Excuse me, sir.
Yes, sir.
Just a reminder, you have 2 minutes left. Thank you.
Sure, sir. A little bit only. On the sensitivity also 92%, sir. It's able to capture and results in a few seconds and in accurate level, sir. That no one propose not at now itself. It's also this shows all results and discussions here, sir, with the tabular column and the conclusions.
Okay, thank you so much for your presentation, sir.
Thank you, sir. This is my reference.
Okay. Dr. Tauhid, any questions?
Yes, thank you. So thank you for the presentation here. So you mentioned about classification here when you do feature extraction and then you do classification. What kind of classifier you have used in your this project here?
Sir, what type of classification, sir?
Well, yes, you said classification. You mentioned you are using classifiers, right?
Sir. Sir, we use CNN, sir.
Yes, you use CNN, but you said you are using feature extraction. It's one of the slides, and then you said plus classifications.
It's a get stuck.
Your voice was cracking a little bit, sir. If you can answer it again.
Sir, so now it's clear?
Yes, now it's clear. You can answer.
Okay, sir. Sir, we use CNN convolutional neural network for get a retinal fundus photography, sir. And we also have 35,000 already captured data sets, sir, that gets compared and we deliver the results. The app delivers the results, sir.
And what is the result for your metric evaluation that you have? You mentioned about metric evaluations, but I haven't seen the result on this metric evaluation.
So don't get understood. What, sir?
Can you ask your question again, Dr. Tauhid?
Sir, can you repeat this?
You mentioned about metric evaluations, about precision and the recall and all of this. So where is the table that represent this metric evaluation to show your approach is good?
Thank you, sir. Sir, sir, just one second, sir. Sir, sir, that in our project, the model achieved, the system is able to correctly identify the severity levels from retinal images that evaluated the model using matrices like accuracy, precision, recall, and F1 scores. That the result shows our models performs well and it's assist in early diagnosis of the disease. It's not get it's not detect it's detect early, sir, not detect after the disease can affect. It's get it's detect early before it's get affected, sir.
Okay, thank you.
Dr.
Thank
Sharma,
you, sir.
any questions?
Question that how you handle image quality issues?
Image quality issues,
Yeah.
sir. Sir, that we applied pre-processing techniques, sir, like resizing, noise reduction, and contrast enhancement, sir. These steps help improve the image quality and allow the CNN model to extract better feature for accuracy classification, sir.
What is the size of your data set?
So size of the data set, sir, 2 to 4 into 2 to 4 pixels.
Any limitation?
Sir, limitations, one second, sir. Size. One second, sir.
Thank you. Thank you.
Thank you, sir.
Oh, okay, no further questions, right?
Mm.
Okay. So that brings us to the end of our session 9F. Give me just a second. Yes, so now I would like to request Dr. Mohammed Tawhid to give us his closing remarks, please.
Sure. I try to just express many thanks to our speakers for amazing and excellent talks and sharing their experience and sharing also their very recent result. It's a real pleasure to have and to see all of this result, and also special thanks for the organizer for this conference and for this session in particular here to make this happen. And we really appreciate this gathering here. And hopefully, I will see you again in near future. Thank you.
Thank you so much, sir. I now request our session chair, Dr. Ajay Kumar Sharma, to give us his closing remarks as well.
Thank you all. I think I sincerely appreciate the effort of all the authors who shared their work today. The quality of research and innovative ideas presented during this session have been truly commendable. Our thanks to all the participants for their active involvement, thoughtful questions. My heartfelt gratitude was once again to the organizing team, core team, Professor Amit Joshi sir, respected Parth sir, for ensuring the smooth conduct of this session. Lastly, I extend my sincere thanks to all the authors for their valuable contribution. Thank you.
Thank you. Thank you so much, sir. I sincerely thank all of our authors for their excellent presentations and contributions towards this session, and all of our participants for being a part of this conference as well. I hope this session was knowledgeable and informative enough for all of us. And on behalf of the team, thank you for the support that you have shown during this 11th version of ICTIS. We would be more than happy to host all of you back in 2027 for the 12th version as well. A small announcement, all the presenters will be getting their digital certificates via email within 2 to 3 working days, and the publications will be live within 7 to 8 months. So please kindly cooperate with the team of ICTIS. And I would also like to thank both our session chairs for chairing this session. This is just a small token of appreciation on behalf of Team ICTIS and Global Knowledge Research Foundation as well. Thank you for your valuable presence. Just a small request, can you please turn on your cameras for a quick snapshot of this conference, please?
Can you just turn on face mode and face alone?
We still have some people. Can all of you please turn on your cameras quickly?
I have a question.
Sure, ma'am.
Can we get to the recording of this presentation?
I am not quite sure. I will get back to you once I confirm it.
Thank you so much.
Okay. You're very welcome now. And we're done. Okay. Thank you so much, everyone. Have a great day ahead.
Thank you, everyone. Thank you, sir.
Thank you. Thank you.
Thank
Thank
you.
you.